every company starts with a vision or a mission or a purpose. We have a very clear sense of the purpose here in KPIT. At KPIT, we firmly believe that science and technology can play a major role in the betterment of the world. And in that in mind, we started working on KPIT Chhote Scientists, which is for school children, then KPIT Sparkle for college students, KPIT Shodh for PhDs. Our tagline, which really encapsulates our vision, is reimagining mobility. What do you reimagine mobility for? For a cleaner, safer, comfortable, greener world. And all the actions that we are doing in this company is to make these things happen. And there are multiple dimensions through which these actions happen. Clearly, a green or a clean mobility is one of the first things. How do we make mobility cleaner? We work in this area to make engines more efficient. We work in these areas to make batteries more efficient. We do a lot of work on hydrogen fuel cells, all of which can come together to make our mobility fossil free. That's as far as the clean part is concerned. We are also doing extensive work on autonomous driving. Now, what do you need autonomous driving for? You need autonomous driving to make driving more safe. A human driver may sometimes make mistakes because there are tensions in his mind, there are distractions, whereas a machine can really track everything that is happening on the road and guide a human driver to do a better decision. There is also a lot of work that we are doing on connectivity. How can we bring information and infotainment to a person who is sitting in a car? Quite a few of us spend a lot of time sitting in our cars, traveling to and fro to wherever we want to go. How can we make that time more productive without causing a distraction? So that's also a part of the work that we do in KPIT. Last and not the least is that we have to recognize that a vehicle, whether it's a car or a truck or a bus or whatever, is a capital equipment. How can we reduce its downtime? So how can we do diagnostics of problems that are either there or are likely to be there? So all this type of work is what we do in KPIT. We are convinced that the world is moving towards better mobility and we want to be in the forefront of that. Our motto is to know automotives better than any other software company and to know software better than any mobility company in the world. With this, we can truly contribute to making the world a better place. We are inviting all of you to join us in this most exciting and educating journey.
Welcome to the KPIT Shodh Awards presentation. I am Rutuja Rane, who will be the host for today's event. KPIT Shodh Awards is an international program launched by KPIT to recognize and honor the individuals and to promote research and development in the field of mobility and energy. Over the period of last few months, we have received hundreds of nominations. After rigorous selection process, we have selected the top entries. So here we are today to present the award-winning entries to you that have truly impressed our judges. So let's hear from the award-winning entries.
Hello, my name is Sashwat Singh. I have recently completed my PhD under the supervision of Dr. Prabir Barkanda from Indian Institute of Science, Bangalore. And right now I'm moving to University of Waterloo for my postdoctoral work under Professor Linda Nazar. I'd like to thank the KPIT Shodh Award team for giving me this opportunity to present my work. This is work titled Structural and Electrochemical Investigation of Bisulfate and Hydroxysulfate-based polaric cathode materials. Now, if you look at the battery community or battery research currently that they focus on, and it's basically on three areas: electrolyte stability to increase the battery life and so that it goes for longer duration for long-range batteries application. And then the second one is to increase the energy density of batteries using novel reaction mechanism such as anionic redox apart from the cationic redox. And the third one is novel cathode, and this is basically the one which I'll be also discussing today. And that one is to create new materials to address some of the challenges that we face today in the battery. And the one is the cost. So we need to have a battery which is economical. That's because 51% of the cost of the battery comes from the cathode. And the second one is to make batteries economical for large-scale applications such as stationary storage as well as electric vehicle applications. And also one has to address the challenges of the limited resources of lithium cobalt oxide based cathode materials. So my thesis is focused in this area, and more specifically, I'll be focusing on the polyionic sulfate based materials, which would have sulfate moieties. So in cathode material landscape, there are oxide and polyionic based material. Polyionic based material have various advantages over oxide, such as thermal and electrical stabilities, as well as voltage tunability. The glaring example of polyionic material is LiFePO4. Now, the first report of lithium insertion in polyionic sulfate-based material was in 1999 with the report of lithium insertion in fake sulfate, which also led to the development of the inductive effect theory, where they found that depending on the moieties, whether it's tungsten or sulfate, the voltage of the redox material can be tuned. However, there was need to increase the redox voltage further, and therefore, highly electronegative fluorine atoms were introduced into the system to get this compound, LiFeSO4F compound. However, since these compounds are hazardous because of presence of fluorine, there is a need to be free of fluorine, and that led to the exploration of lithium metal bisulfate compounds. Now, these family of compounds, they basically have two polymers, monoclinic and orthorhombic, and depending on little structural differences, they will have crystallographically similar lithium, otherwise crystallographically two different lithium sites, and that will lead to different reaction mechanism as well as little differences in the redox potential. Now, based on that, if you look at the polyionic sulfate-based materials, they have a rich crystal chemistry and they are known for low temperature of synthesis. And because of that, we wanted to unveil newer cathode materials and see what are the possibilities. So if you look at the lithium metal bisulfate compound, there is a possibility of metastable phases for some analogs of compound. For example, in case of nickel, there's a possibility of monoclinic phases. Now, since these compounds were earlier made through energy-intensive routes such as ball milling, otherwise mechanical-chemical synthesis routes, these metastable phases were not stable, and therefore there was a need to find some new synthesis approach. Now, based on that theme, my thesis is presented here. The first one is lithium nickel bisulfate-based compound, which I have explored, and then there's a Na2CuSO4 based cathode materials. The third one is mineral-inspired antiphylite-based NaPSO4 compound, and the last one is the moisture-resistant, environmentally benign hydroxysulfate-based compounds. So, to synthesize that metastable monoclinic phase of nickel analog, there was a need to use some soft chemical approach, and therefore we went towards spray-drying synthesis routes, and with the help of this route, we have synthesized this compound at a low temperature of 305 degrees Celsius for 10 hours. As you can see, the phase period is very high. And moving ahead, we then extended this route to other members of these compounds. Because of the nature of the route, we got a very spherical morphology, and also we see that the crystallinity is very high. So if we compare the phase stability or the enthalpy of the two phases, that is monoclinic and orthorhombic, we see that very little difference in the enthalpy, and that was the reason why metastable monoclinic lithium nickel bisulfate compound was not synthesized earlier with the routes which were highly energy intensive. This lithium nickel bisulfate compound basically offers a two-dimensional pathway for lithium ion migration as calculated from the point valence site energy calculations. And the migration would be 0.47 electron volt. However, more precise values can be obtained through rigorous DFT-based calculations. Now, since nickel is known to offer a very high redox potential, whatever attempts we made to study the electrochemistry was in failure, and therefore we took help of VFT-based calculations to look at the voltage and what will be the mechanism that will be involved. So we see here the density of states at lithium 2, 1, and 0, and all along we see the high contribution of oxygen 2p orbitals near the Fermi energy levels, and that indicates the electron compensation will occur from the oxygen 2p orbitals. So in all, this material is a high voltage 5.5 volt material, which will employ an anionic redox for the electron compensation. These can be tested in ionic electrolyte and other highly stable, salt concentrate based electrolyte. Now, going ahead, there are cyanide and chromite based duo, which are basically the minerals, and they are basically known for their thermochemical energy storage. You can heat this compound to get the dehydrated phase, and then you can again provide water to get back to the hydrated phase. And in that way, one can store thermal energy. However, since they are found in nature, now we wanted to synthesize this in lab and see the structural and crystal chemistry. So with the help of split-line route, we again synthesize this compound, and we see from the inoperative study that at about 150 degrees Celsius or so, the dehydration occurs to the selenite phase with a change in the morphology. And in reverse, when we do hydration from selenite, the hydration follows a course model where the hydration happens very fast initially and then it slows down. The high structural reversibility comes from the copper, comes from the structure. As you can see here, initially in the hydrated phase, there's a glue, hydrogen bonding based glue, which holds the structure together. However, once this glue is removed, the structure breaks down. And this is further, the further problems comes from the zone directivity of copper, which makes the dehydrated compound very low in symmetry. Because of the absence of any migration pathway, inertial chemistry could not be tested. However, the conversion-based chemistry is possible in copper-based system, and therefore we took this compound to a very low voltage to see if conversion chemistry based energy storage can be done. And the first discharge capacity is quite high. However, further optimization is needed to get any meaningful energy storage in this compound. And the cause of irreversibility is probably the copper ion migration, either into the electrolyte or to the lithium sides. Now moving ahead to my third area, it is the mineral-inspired endophyllite-based layered NaVSO4 compound as a cathode for lithium and sodium batteries. Now in this family of compound, the first compound which was reported as cathode was NaFeSO4 from Gordenev group, and it was found to show a solid solution reaction at 3.21 volt for sodium storage. In another study, it was found that one can achieve higher energy density if one can have two electron reactions in this family of compound, and that was only possible in vanadium or titanium based analogs. And so we went on to answer this question whether it's possible or not, and we synthesized this compound through a solid route and checked its phase purity with the reticle analysis, and we see that this structure is a layered structure where the lithium or sodium sits in between the layer, and the incoming guest ion can sit in these positions. So from BVSC analysis, we clearly see that the incoming lithium or sodium ion will be sandwiched between the host sodium as shown here, and overall the material would offer a 2D pathway for sodium or lithium ion migration. Now further, from the DFT based calculation, we proved that all along the reaction, that is two electron reaction, the vanadium would be the redox center. As seen here, the increased contribution of vanadium 3D orbitals near the Fermi energy levels. However, the experimental evidence of the second electron reaction is still lacking. Now, through electrochemistry, we were able to prove the one electron reaction. However, the second electron reaction couldn't be achieved because of the electrolyte stability. But for the one electron, we see that it will follow a solid solution reaction, both for lithium as well as sodium ion, proving its versatility. However, rate kinetics is lower for sodium compared to lithium. And from PITT-based data analysis, we see that a classical quaternion type current relaxation behavior, proving that the reaction mechanism is solid solution reaction. And further, this is again supported with the help of ex situ HRD-based analysis, as well as the presence of vanadium as the redox symptom with the help of XPS-based ex situ XPS-based analysis. And further, the rate kinetics as seen here is that it's slower for sodium compared to the lithium, and this could be because of the bigger size of sodium. Now going ahead, in order to remove fluorine from LiFeSO4F based system, one can get FeSO4OH based system. Although the redox potential will come down, the material will become much more moisture resistant, and also it is thought to be in KP9. Apart from that, these compounds can be synthesized at a very low temperature that makes them very economical, and their precursors are also very sustainable. So the first compound from this group was a monoclinic FeSO4OH that was reported in 2009 by Valerie Plow group, and it acted as a 3.2 volt lithium-ion battery cathode. And later on, its polymorph monoclinic LiFeSO4OH showed a solid solution reaction. So the mechanism changed from a sharp biphasic reaction to a solid solution reaction mechanism. And also, the literature we found that there is an orthorhombic FeSO4OH which remains unexplored. And so we wanted to see what would be the effect of the different structure on the reaction mechanism. And further, we wanted to repurpose this monoclinic phase as a cathode material for sodium-ion batteries. So we really inserted sodium in monoclinic FeSO4OH, and we see that the rate kinetics is very slow, and it occurs at a C by 100, and we could only insert 0.7 mole of sodium in the system. And even with the very slow rate of equilibration also, one cannot achieve higher capacity, and that indicates the structural limitations. However, we found that the reaction mechanism has changed here from earlier two-step to now single-step biphasic reaction mechanism. And why that happens is because lithium can be stable in both octahedral as well as tetrahedral phases, whereas sodium would only like to be stable in an octahedral environment. And therefore, when sodium goes and sits in these kind of tunnels, it cannot accommodate to sodium as it did for lithium, and therefore we only see one step of the reaction. Further, we unveiled orthorhombic FeSO4OH as a novel independent cathode material for lithium-ion batteries using a very low temperature hydrothermal synthesis route. And as can be seen here, it's a phase 12 compound that is made, and the lithium migration in this compound will occur along a direction perpendicular to the B-axis, or it will be contained in the AC direction, AC plane. And further, with the help of synthesis variation, we found that with increasing temperature time, only 0 to 0 plane will be the preferred plane for growth. Now, once again, the lithium insertion goes through a very sharp two-step biphasic reaction as shown here, as also proved from the PITT curve, where the current relaxation is non-contrail in nature. Compare that with the orthorhombic FeSO4OH, where the first step is showing a little sign of biphasic reaction. However, the solid solution region is more. And from the next step onward, or in the next subsequent cycles, it follows a solid solution reaction mechanism. And that probably happens because of a distorted kind of tunnels as you see here, as there is a structural variation where the tunnels are partially blocked by the sulfate units. These are proved with the inoperant oxide as well as supported by the excited oxide. So with that, we come to the highlights of the work, where we first unveiled a monoclinic new phase of lithium nickel bisulfate with using a novel approach of spread and synthesis route. And then with the help of Solger route, we have looked at the new compound which acts as a cathode material for lithium and sodium-ion batteries, and there is a possibility of achieving high energy density by applying two electron reaction. And then we have unveiled an environment KP9 orthorhombic FeSO4OH as a cathode material for sodium and lithium-ion batteries. And further, throughout my thesis, I have taken help of some inoperant accelerated fraction, and I've also done magnetic analysis and structural solution. And also, I have taken help of some of the radical analysis tools, etc. So these are my accomplishments: some journals, some book chapters, conference proceedings, intensive for 6 months in France, and some of the synchrotron facility uses that I have done for my thesis. These are some of my conferences that I attended. And so in the end, I'd like to thank my supervisor, Professor Pranay Panda, for creating an enriching environment and giving me a very good time through 5 years for during my thesis. And these are some of my collaborators. With their help, I could solve some of the problems in my thesis. And I'd like to thank my research funding agencies. And at the end, I'd like to thank KPIT Shodh Award for giving me this opportunity to present my work with all of you. Thank you very much.
Hello everyone, myself Rishabh Das, and I am working under Professor Sebastian C. Peter at JNCSR, Department of New Chemistry Unit. First of all, I want to thank the organizer for shortlisting me for the award of KPIT Shodh in the sector of green energy generation. I applied for this particular topic because I am working on photocatalytic CO2 to fuel generation, and my thesis was entitled as Design and Development of Metal Oxides and Chalcogenides for Solar Fuel Synthesis from Carbon Dioxide. This number is a very problematic number. What this number represents and why this number is scary. If you see the CO2 level in the atmosphere, the pre-industrialization era, the level was less than 300 ppm. However, today it is 419.19. That's why this number is very scary. If we allow it to increase like this way, it will become a real problem for the society. We can compare this a kind of hockey stick model, which we have seen during COVID-19. This peak was in May 2021, where you can see the increment of COVID-19 cases were similar like the increment of CO2. So we can say the quicker we will take a measure, or we will take some steps to reduce the CO2 amount, we will be in a safer hand. But today, we will not talk about the problem, rather we will talk about the opportunities. What are the opportunities related to this? If we can use the extra amount of CO2 and we can convert it to fuels, we can solve the issue of energy, because to run a society we need a lot of fuels, and nowadays we are more going towards the renewable fuels rather than the normal fossil fuels. And why now the question is solar energy? Because the solar energy has a lot of potential. A simple calculation will clear this fact. The number of energies coming to the Earth's surface is 4.3 into 10 to the 20 joule per hour, and we need energy to run our society is 4.7 into 10 to the 16 joule per hour. So if we can harvest the extra energy for 1 hour, we can sustain 9,200 hours. So if we see the current geopolitical scenario, we should be an energy independent country. However, currently we are importing $168.6 amount of fossil fuels from outside. So if we can generate our own fuels from renewable energy source, we will become an energy independent country, and we can solve the issue of energy and environment together. However, the process is not so easy, because we need a good photocatalyst to overcome this extra activation barrier. How this photocatalyst works? Upon irradiation, it generates electron and holes. This electron performs CRR in presence of the oxidized protons. And in this particular process, the problems are recombination of these electrons with the holes and the solubility issue of CO2 in water, because we do the catalysis in water medium. Another problem is completing hydrogen evolution reaction, and this particular field is in nascent stage, therefore a lot of things are unknown, like electron transfer mechanism, product formation mechanism, etc. If we see what are the products possible from CO2 reduction and their current market price, you can see the C1 product has lesser market price compared to multi-carbon products. So our aim always was to get more multi-carbon products like C2 products or C3 products. So to stop the recombination, to get more multi-carbon products, the scientists are basically using, instead of one semiconductor, they are putting two semiconductors together so that the recombination process can be stopped. Another way is to use the organic additives, which will take away the holes and the electrons can be stabilized to do more CO2 reduction reaction. These are the products possible from CO2 reduction. However, the C2 and C3 products mainly obtained from electrochemical pathway. Photochemical pathway only generated C1 products. But in our case, with our investigation, we could able to generate some amount of C2 products. And recently, some reports are there where people have reported some amount of C2 products. Let's see how we have tackled the problems. So already I have given the introduction, and we also have worked on the pitfalls of photocatalytic CO2 reduction. In next chapter, we have discussed about the heterojunction, as I mentioned. So with that, we can stop the recombination path. With that, we got methane and methanol as a C1 product. Later, we played with the charge polarization, and then we got ethanol as a major product. Next chapter, we have improved the ethanol formation by employing very low-cost red phosphorus material. And finally, we made a organic inorganic heterostructure, and with that we got ethylene as a major product. So as I mentioned, this TUA and acetonitrile, this kind of organic additives people are using to improve the CO2 reduction efficiency. However, in our study, we found these solvents can undergo photolysis by itself and give rise the similar product which we are expecting from CO2 reduction. Therefore, these are the overestimated product. We have quantified those things and we have come up with an idea that what are the light source region and what are the solvents can be used in which kind of region. So we can say if we are using this kind of organic solvent, we should not illuminate them in the UV light, and ethyl acetate should not be used to perform CO2 reduction or HER. This particular study is not only helpful for CO2 reduction community, rather it can be helpful for those who are studying different kind of solvents and handling the UV light. Next chapter, we have tried to understand the heterojunction, and we made bismuth vanadate and tungsten oxide, this kind of heterojunction, where we found the strain has been relaxed because of bismuth bond distance increment, which we have understood from EXAF studies. And when we performed the CO2 reduction study, we found very high amount of yield with a nearly 100% methane selectivity. With the composite 1,4, we found almost like after 220 hours also the activity is still there. Then we have explained the electron transfer mechanism from tungsten oxide side to bismuth vanadate side, from bismuth L3 Zen spectra, and from DFT and drifts in situ IR studies, we have estimated the reaction is going through the format pathway, not through the carbide mechanism. In the next chapter, we have activated TiO2 in visible light, where we have mainly exposed titanium 3+, which is more active sites to bind the CO2 in the oxygen vacancy, and therefore we found more improved CO2 adsorption, and thereby we got better result. And in the composite 2,1, we got methanol as a major product. Here you can see upon the protonation in this oxygen center, we got methanol as a major product. Up to now, we have majorly exploited the heterojunction system. However, the single system also can give the C2 product if we can engineer the catalyst. So therefore, we have made bismuth 19S27Cl3 catalyst, because this particular material has 3 different kind of bismuth center, and which we have proved from EXAPS and XPS analysis. In this particular study, when we have done COTPD, we found in case of Bi2S3, there is only one kind of CO adsorption. However, for Bi19S27Cl3, there is 2 kind of CO adsorption. One CO desorption is at higher temperature. That means some bismuth center is there. These are absorbing the CO more stronger way, and these CO are actually coupling between each other and giving the multi-carbon products, which is ethanol over here. On the other hand, the other bismuth site, which is bismuth 3 over here, is staying as it is and performing CO2 to CO production. However, for Bi2S3, we got only CO as a product. Therefore, because of different polarization in these 2 bismuth center, we got ethanol as a major product. Next, again, by importing very low cost red phosphorus material into bismuth molybdenum oxide, we have improved the CO2 to ethanol formation efficiency very largely. And you can see here, we have peeled the red phosphorus surface, and there we have deposited the bismuth molybdenum oxide, and in the composite 2,1, we got the highest activity as per now whatever is reported. From this, we got influenced and we have studied the material in the direct sunlight, and it is performing well in the direct sunlight in different weather conditions. Later, our motto was to understand why this ethanol formation is happening in this particular kind of catalyst. And from primary kinetic isotopic studies, from different kind of control study like as a feed methane and methanol, we have proved that this is a OCH3 kind of coupling reaction is happening, and which we again proved when we have employed deuterated methanol. We found these hydrogens are deuterated. However, these hydrogens are normal protons. From there, we proved it is a OCH3 kind of coupling reactions. Next chapter, our motto was to get much more C2 products. Therefore, we have used this carbazole based organic moiety, and we have used IN 2.77S4, where two different kind of indium centers are there. Because of that charge asymmetry, two different kind of CO and COH has been generated, and because of the close proximity, they are getting coupled and giving ethylene as a major product. From XPS, we have proved the presence of indium 3 plus and indium 2 plus. We have also performed ZENS and EXAPS. From TRPL, we proved that in this kind of composite system, the electron has been stabilized in the conduction band for more time, and we are getting more lifetime, which was reflected from the improved photocurrent generation in the composite material. Here also we have proved from theory that the composite material can activate the CO2 much better way compared to the normal or pristine IN 2.77S4. Therefore, the improved activity has been obtained. From DFT calculation, for the first time, we have proved how CO2 to CH4 has been formed, and almost 10 different energy profile diagram has been produced, and from there, the best were chosen for CO2 to ethylene production. Here you can see, in this particular case, if the reaction tries to go towards a C1 product formation, the energy is very high. Therefore, we are not getting any or very less amount of C1 products. Rather, it is going towards the CC coupling reaction, and then finally it is stabilizing this carbon and carbon bound intermediate, which is giving the responsible for production of non-oxygenated hydrocarbon, which is ethylene over here. If we could have seen this kind of oxygen bound intermediate as a stable intermediate, we might have got some oxygenated product like acetic acid or ethanol. However, as this was stabilized from the which we proved from the DFT calculation in collaboration with Professor Abhishek Singh from IISc, we showed that the ethylene formation is much more facile in this kind of catalyst surface. In summary, we can say we have worked with different pitfalls of photocatalytic CO2 reduction when we are using TEOA, acetonitrile, TEA or ethyl acetate as organic additives. We have played with the pH and strain in the next chapter, and we have made a heterostructure like this. With that, we got methane as a product. Then we again work with a heterostructure model with bismuth, molybdenum oxide and titanium dioxide, and we got methanol over here. Upon charge polarization technique, we got ethanol, and then ethanol was again improved in case of composite catalyst where red phosphorus and bismuth molybdenum oxide was used. And finally, we have worked with a carbazole based porous organic polymer and indium 2.77S4 spinel structure. With that, we got ethylene as a major product. So far, whatever the catalyst I have shown, they are very high performing catalyst. If I specifically take the name red phosphorus bismuth molybdenum oxide for ethanol formation and IN 2.77S4 POP for the ethylene formation. However, this catalyst cannot be directly commercialized right now because of the inefficiency of the photocell. Rather, what we can do is we can work in the interface of photo and electrocatalysis, which is called photoelectrocatalysis, and in the interface of photo and thermocatalysis, which is called photothermocatalysis. In the photoelectrocatalysis, if we use flow cell like electrochemical process, the activity and the current density can be improved, and there is a chance that at relatively lower potential, we may get the multi-carbon products up to C3 product also. For that, we have fabricated a photo flow cell like this, where we can directly use carbon dioxide. Therefore, there will not be a problem of CO2 solubility, and we can get much more product. In photothermocatalysis, we can use a plasmonic photocatalyst, and therefore we can generate a very high local temperature by putting the light energy, not giving the temperature by using the normal electricity which coming from the fossil fuels. So by these two technology, we can use the sunlight and we can perform the catalysis much better way, and this kind of process can be commercialized in the coming future. These are my publications like ACS Catalysis, ACS Energy Letter, ChemCom, Energy and Environmental Science, JAX and Advanced Material as a first author. And as a co-author, I have published these papers. Finally, I want to thank my research supervisor, Professor Sebastian C. Peter. Without his guidance, I couldn't have reached this far. And these are my lab mates. I also want to thank all of them. And this photograph was taken in a facility called Breathe, is a startup where we perform CO2 to methanol with large scale. And interestingly, during the initial stage of this startup, I was also involved here and I have performed a few testings. So therefore, I have a hands-on experience in working as a technology transfer process. I also want to thank Desi Germany for giving the chance to perform exhaust measurement, JNCSR and EST for funding. And finally, I want to thank KPIT Shodh Award organizers to give me the opportunity to present my work in front of all of you. And thank you, all of you, once again. Thank you.
Welcome all jury members. I'm Sandeep Pidwai, presenting the topic on applications of Markov chains and convolution neural network for cognitive reading. Under the guidance of Dr. Uday Wali sir, my research center is KLE MS Sheshagiri College of Engineering, Belagavi, Karnataka. It is under the Vishweshwarya Technological University, Belagavi. So here are my contents. As per the 8 pointers instructed by the coordinators for this conference, as I will go through in new disruptive concepts, innovation introduced, depth and thoroughness of work, scientific and technical understanding reflected in the data analysis, publications and paper quality and quantity, potential for immediate commercialization, technical quality presentation, network collaboration. So as time is limited, I'll just go through the brief of the work done. In this research work, we especially work for the cognitive radio system, which is a smart electronic communication system, or we can say wireless communication systems, which works on the wide spaces in the spectrum. So for that, the spectrum sensing is one of the vital state and first and foremost state in which we need to know the wide spaces status in the spectrum, available spectrum. So we need to have certain infrastructure in place. So we designed then a specific antenna, which is for GSM band, and we have captured the real-time signals from that band. So the first step for this work is to customize hardware antenna for real-time spectrum analysis. Second one, we built the end-to-end accurate spectrum sensing system with a spectrum analyzer, antenna fabricated, design, and the application which we have used, we have designed for a specific band, for the specific signal to capture from the RF band. Next one is design efficient learning algorithms to predict the spectrum utilization using the various deep learning algorithms. And the last one is develop and tested the multiple deep learning models. So here is the first invention in which we have designed the specific application for the various RF frequency bands, and we can have the real-time spectrum on that application. So this particular GUI indicates the real-time spectrum scaling on which is similar to that of the hardware spectrum analyzer. But here the specialized thing is that we can have the real-time spectrums as well as its power levels listed, which is listed to the left side. So a signal power level can be captured total of around 501 samples at a time in one scan. So here we can easily observe this particular application provides the various as per the settings and as per the configurations, we can have the different antenna in place and we can change the band. So this application becomes a universal application for data capture. So objective was to know the available spectrum in real time. So this is a methodology which we have implemented for various deep learning algorithm, which is common and it is an industry standard methodology. First, we have collected the data, cleaned the data. That cleaned data is in order to apply to the various model for training. We have applied it, divided it into train and test data. Training data is applied to various models MLP, autoencoder, LSTM, and convolutional neural network and Markov. These are the 5 models that we have used for prediction. So out of that 5 models, we come up with the prediction and tested with the or checked with that particular test data, compared that results and compare their accuracies also. So from that, we come up with a kind of ideal model suitable for the RF spectrum data. So this is one of the location-wise data which is available because we have collected 4 different places. We have the data. We have collected the data from the 4 different locations, and we came up with that particular status of that spectrum by plotting it with a 3-dimensional way. And we came up with this particular power levels of each and every locations for particular duration. So these are the histograms indicating various channel status for uplink as well as downlink. As we are aware of that, GSM band has 2 different bandwidths or bands in which we can say there is an uplink and downlink. Uplink is connection between the user and the base station, and downlink is the connection between the base station to the user. So there is a difference between 2 different bands. So naturally, this particular number of channels are from the downlink channels, downlink bunch, and they indicates the power levels at respective ranges. Now here we can take an example of the 326 channel number. It indicates the power level between -80 to -60. So this is the power level in this particular channel for this number of samples. So for every channels, we plotted the number of samples in that different power levels. So this is the pattern or the CSV file that we have prepared after cleaning the data. So minimum, when we say there is a one particular data set, it has the minimum of 5 million samples, and for single channels we have used 1077 samples. A total 351 channels that we have assessed. Total 25 channels. For that we got 19,024 samples for the duration of 5 hours. So this data has been categorized into 3 categories. First is occupied, which is a power level greater than -70 dBm. Second is unknown, that is -70 to -80 dBm. In between that, and unoccupied state is it is above -80 dBm. So these 3 categories are being preferred for classification purpose in the various deep learning models. So this is a generalized GSM range for uplink, and this is a downlink range, and the channel separation is 200 kilohertz. Now these data captured we have stored at a GitHub repository on this particular link. Researchers can refer this link for downloading this data for future work. Now, in next category of the depth and thoroughness of the work, we come up with this particular 3-state Markov model, in which these 3 states are indicated with O, W, and U. This is a 3-state probabilistic model, and it creates probability maps for every state of the system from the training data. And the outcome of this particular model is with the 3 different matrices. That is, first is the initial matrix, second is a transition matrix, and third is a probability matrix. So when we accomplish the parameters for verification of this particular model, we come up with these parameters like accuracy, MSE, RMSE, and MRE to check with the performance. And now these particular aspects that we have performed is easily accomplished with the help of binning of the input data into the states of the system. So it is a classification application that we can use it with the Markov model. So Markov model in scientific and technical understanding of which is reflected in this particular data analysis that we got is the transition matrix, which is one of the vital important for the Markov model. And this particular plot shows the transition from the occupied state to other states, that is white spaces and unknown states. So if you can see the trend of this particular graph, after a certain period of time, this becomes a particular flat representation, which indicates that there is a Markov model probability becomes constant for after certain period of time. So this is the histogram showing the different channel numbers, and for that different number of channels, this is a histogram showing the power levels from minus 90 dB to minus 60 dB, right? So this is the plot which is plotted by the Markov model for the downlink channels occupancy status, showing the different channels at one particular location. So this is one of the important models for this particular research work, that is convolutional neural network model, which has the convolutional as well as convolution layer, in which we can come up with these particular dimensions for respective layers. We use this particular convolution plus ReLU layer at the input, average pooling, fully connected plus ReLU, and softmax. So at the softmax is considered to be the output layer, in which we are going to make use of this particular input data to be converted into 3 categories of that data, as we have already defined. So Y1 cap, Y2 cap, and Y3 cap are the 3 different categories at the output that we are going to get it. So this is the overall CNN model architecture, in which there are 2 convolutional layers and 2 ReLU layers are being 2 average pooling layers are being used. So we came up with this output of the CNN model, that is kind of the MSE plot as well as accuracy plot. Along with that, we have got a occupancy predictions of the CNN model. So for MSE response, we easily come across this particular reduction in the mean square error, which is considered to be the ideal case of any performance of the model. And along with the number of epochs, this particular MSE goes on decreasing. Next is an accuracy response, in which the CNN model provides the higher accuracies as we are going on increasing the epochs. So these are the 2 responses that we got from the CNN model for specific data set. Now this is the predictions that we got, actual status and the predicted values. This prediction set that indicates the prediction of the by the CNN model of the respective particular sample sequences. Now, performance evaluation of the LSTM model that we have also considered, as we are going to consider the comparative analysis for the various deep learning models in order to make use of this particular comparative analysis for coming across the best model out of this comparison. So for LSTM, it is considered to be the various units considered from the 16 units to 64 units, and we have plotted this plot for with respect to the epochs and MSE. So we have got this particular depends on the number of units. The MSE is varying from a certain value to a lowest value. So the 1024 units, for 1024 units, it is plotted that the lowest MSE is found to be there. And this is the plot which is indicating the variation of the performance of the LSTM model based on the training and testing data. So a blue color indicates the ground truth, and orange color indicates the training data, and green color indicates the testing data. So my publication for this particular work is 4 international journal publications and 3 conference papers. So you can see this international journal publications in 2016, 2019, 21, and 21. 4 publications are in the respective year. And conference publications are in 2018 and 2 in 2020. So these are the recent citations for respective title of my publications. So we have compared various models, but among them, we have compared the Markov model with the CNN as well as LSTM model, which is found to be the suitable model and providing the higher accuracy for this particular outcome. So you can easily come across after comparison that accuracy for CNN model is found to be 99.15%, which is comparatively higher as compared to the other models. Okay, so this is a prediction accuracy comparison of the Markov, CNN, and LSTM models. This comparison was for uplink channels, and this comparison was for the downlink channels. So you can come across this particular CNN model accuracy is 86.04, which is higher than Markov as well as LSTM model. So this accuracy indicates the considering the predictive accuracy for comparison for these three different models. Okay. Now this is the plot, or this is a table showing that particular parameters for these 5 different models. So we have compared all 5 models for 25 uplink channels and 25 downlink channels. So these are the 8 different parameters for which this comparison has been carried out. So the potential of the immediate commercialization, we can say that this concept is under the filing. We are filing the patent for this particular concept, and we are in making use of this particular concept for industry ready product. So the system can be developed on cheaper hardware. This is one kind of thing that we can make it out. Real-time prediction of the channel occupancy, effective utilization of the bandwidth, improved end user connectivity. So these are the parameters that over which we can easily come across these particular commercialization aspects. Network collaborations. We have collaborated with the Sequad Software Belgavi, Karnataka to design the spectrum sensing applications. These are our conclusive remarks that it is possible to capture the entire GSM band using the application design in this particular research work. Neural models are found suitable for the spectrum prediction purpose. CNN and LSTM these neural models are found to be good for a choice for the spectrum prediction application. And the neural model used in this research work can help in effective operation of the cognitive radio in terms of the accurate predictions of the spectrum occupancy. Thank you very much.
Hello everyone, myself Daswandi Sawant. I am here to give a presentation of my thesis titled as Robust Control Strategies for Autonomous Vehicles in Uncertain Environments under the guidance of Dr. U.N. Chaskar, College of Engineering, Pune. So my Shodh ID is IN Shodh 2000057. So to start with, I'm going to explain the automation levels. So the Society of Automotive Engineers, SAE, has defined 6 levels of driver assistance technology advancement based on the amount of human involvement in driving tasks. So it starts with no assistance as level 0. Then in level 1, it's a driver assistance assisted functions such as ABS, anti-lock braking system. Then in level 2, it's partially automated. So the functions include adaptive cruise control, lane keep assist. Then level 3 is conditionally automated, where the driver is required but does not need to monitor the environment all the time. He must be ready to take control of the vehicle with notice. So the examples of level 3 automated cars will have traffic jam pilot, parking assistance, cooperative adaptive cruise control, which is called as CACC. Then level 4 is highly automated, where the vehicles can perform all the driving functions and the driver may be able to control the vehicle whenever the system asks to control. And in level 5, it's fully automated vehicle capable of performing all the driving tasks under all conditions. So it is entirely autonomous vehicle even in case of all emergencies. So, to establish the control of autonomous vehicles, primarily we need to control two types of motion. So, first is longitudinal motion, second is the lateral motion. In longitudinal motion, the forward motion control within the lane needs to be established, and in lateral motion, we control the motion when the vehicle is moving from one lane to another or taking a turn over the curvature. Now, why we need to control the longitudinal motion? So, for my research work, I have developed control of the longitudinal motion of autonomous vehicle because it has a potential benefits of improving traffic throughput, highway safety, fuel consumption, and emission. Emission can also be reduced. Now, these issues are being addressed in autonomous vehicles through some of the existing solutions, so which are shown here right now. So, first is a cruise control. What happens in cruise control is it reduces the load on human driver while driving on highway. So, cruise control was introduced whereby one can set a speed at which the vehicle should accelerate, so the driver does not require to command the pedal action all the time. Then in adaptive cruise control, two modes were introduced where the user can either set a distance between the two vehicles, or it can set a distance between the two vehicles, or it can set a speed set point. So when there is no vehicle in front, it will go to cruise control mode, and if and the vehicle runs at the set speed. And if there is a vehicle in front of the host vehicle, it will switch to the distance control mode by following the preceding vehicle speed at the safe distance. Then we have intelligent cruise control. So it is also known as smart cruise control with stop and go function. So this will apply the brakes and will bring the vehicle to complete stop if the vehicle ahead slows down to a complete stop, and it can also accelerate to the set cruising speed. So this is most beneficial in rush hours or in traffic cases. Then next we have is predictive cruise control. So it uses the navigational data like GPS, then sensors such as cameras, radar, lidar, and in this control the system will know which driving condition needs to be considered over the next 1 or 2 kilometers, if there are bend, crossroads, or speed limitations on the road ahead, or so the car will amend its speed accordingly. Then in cooperative cruise control, this is the, I would say, advanced version of ACC, where the pattern of where the platoon of vehicles is moving synchronously with a set speed for all vehicles. So in CACC, there will be one leader vehicle and there will be another vehicle which will form the platoon, and the leader can be manually driven or an autonomous vehicle which utilizes onboard sensors, and it will detect the preceding vehicle position and speed. Now in addition to that, it also utilizes vehicle to vehicle, that is V2V, and vehicle to infrastructure, that is V2X communication. So in V2V, the acceleration command of preceding vehicle and the braking command will be received. Now with V2X, the information from the signboard, speed limit, the curvature, slope ahead, all these information will be received via GPS, with the help of GPS. And all these V2V, V2X information is received through the wireless network system. So now that's the basic of the longitudinal motion automation levels of SAE. Now coming to my disruptive elements of my PhD work. So I have developed new control strategies for controlling the longitudinal motion of a platoon of autonomous vehicles. So along with that, I've also achieved the string stability of a platoon as well as individual stability of a vehicle. And in turn, the traffic throughput, vehicle safety, and possibly fuel efficiency is also achieved because we are compensating the effect of parametric uncertainty and some unknown external disturbances. Now, these are the environments which we have considered, and we have developed a robust solution, robust control strategies for all these environments. So, wherein we have considered homogeneous and heterogeneous platoon. That means the number of vehicles in a platoon can be of similar type, that is having same time constant, or can be of different type. So, that would be heterogeneous platoon. Then we have also achieved a stable solution in case there are uncertainty in actuator dynamics, in case there are communication and actuator time delay. If the vehicle to vehicle communication is not there, if it is not received properly, in that case also we have developed a control strategy. Then in case of cut-in cut-out maneuver, so cut-in means in a platoon, if any vehicle is becoming a part of a platoon, and cutout means any vehicle which is a part of a platoon is taking exit from the platoon. So in both these situations, we have implemented control strategies. Along with that, we have considered different information topologies like multiple predecessor information if we are receiving. Then in that case also we have developed the control law, and if there are non-zero initial condition, in that case also we have implemented the control strategies. So the major work of all these uncertain environments and all the strategies are in these 5 achievements has been tagged. So first is we have implemented the state feedback control for CACC. Then adaptive cruise control and cooperative adaptive cruise control we have implemented on a car scene. Then we have also developed the disturbance observer based sliding mode control for cooperative adaptive cruise control system. And then nonlinear disturbance observer based sliding mode controller we have developed for cut in cut out maneuver. And then in last, disturbance observer based super twisting control we have implemented for CACC. So in methodology, we have used the different control strategies. So we started with implementing the traditional sliding mode control. Then we enhanced it with disturbance observer based sliding mode control. Afterwards, we also implemented the super twisting control, and we implemented it with non-linear disturbance observer based super twisting control. So in disturbance observer, the estimation of a preceding vehicle acceleration and parametric uncertainty present in the vehicle dynamics have been estimated. So initially with linear disturbance observer, and the performance of the linear disturbance observer have been improved with non-linear disturbance observer, and it is combined with sliding mode control and super twisting control. And then we have also considered a spacing policy, like we have considered constant time headway policy, because while designing the cooperative adaptive cruise control system, the spacing policy will decide the desired distance between the two vehicles of a platoon. So this desired distance is velocity dependent, so it is called as a constant time headway policy. Then the information flow topology is defined because the way the autonomous vehicles obtains the information from other autonomous vehicles in cooperative adaptive cruise control. So in this proposed work, we have predecessor following information that has been utilized for implementation of a control, which utilizes very less information over a wireless communication network as compared to predecessor leader following and bidirectional information topology. Uh, Now, string stability. So, what is string stability? It is required to ensure that the either the vehicle spacing error states or the control input do not amplify in the upstream through the platoon. So, if the platoon is not string stable, a small perturbation on one vehicle can propagate through platoon and may cause an uncomfortable driving experience. So this string stability of individual vehicle as well as of the entire platoon is also necessary, and that also we have achieved. Then all these schemes are implemented on MATLAB Simulink, and some of these control schemes are validated on a nonlinear simulation tools like Simulink, CarSim. Then comparison of with existing results. So the performance of proposed scheme has been compared with existing techniques like proportional derivative controller, sliding mode controller, or constant time headway based controller. And we have found that the selection of headway time constant is not dependent on any vehicle parameters, and one can select smaller headway time constant as compared to traditional scheme, which in turns increases highway capacity with our scheme. So that improves the advantages of our scheme, where we are removing this restriction of selection of headway time. These are my publications. So in the transportation, in the IEEE transaction on intelligent transportation system, there is one paper that has been published, which titled as robust control of cooperative adaptive cruise control in absence of information about preceding vehicle acceleration. Then the second paper that has been published in the Proceedings of Institute of Mechanical Engineers, Part D, Journal of Automobile Engineering, SAGE Journal, and it is titled as a nonlinear disturbance observer based cooperative adaptive cruise control for real traffic scenarios. And a third paper, which is a nonlinear disturbance observer based super twisting control for cooperative adaptive cruise control system, is under revision. It has been submitted again to the Proceedings of the Institution of Mechanical Engineers, Part D, Journal of Automobile Engineering, SAGE Journal. These are the two international papers that has been published in the international conferences. So first is about the state feedback control of platoon in presence of parametric uncertainty and communication delay. And the next one is development of cooperative adaptive cruise control with multiple predecessors information and CARSIM validation. So the last point of which I would like to cover is about potential for commercialization. Now, the cooperative adaptive cruise control system is implemented so that the highway traffic flow, fuel efficiency, and string stability can be improved. Now, if the human driver creates a platoon, then there will be reaction delays, which will cause frequent acceleration and braking command. So the advantages of CACC system is it decreases the following distance between the two vehicles, and it will allow more vehicles to fit in a lane. It will also increase the string stability by attenuating the attenuation of traffic disturbances in the upstream direction. So overall, we will get a good highway environment and more efficient state of operation. So that's the potential for commercialization. Thank you so much.
Good morning, everyone. I am Subhat Vishwas, and currently I am pursuing PhD from IIT Kharagpur under the supervision of Professor Siddhartha Mukhopadhyay, and my research topic is hierarchical supervisory control for energy management of hybrid electric vehicles. So, why in this EV revolution, why exactly AGVs are required? So we have some data from the market, So we can see that here there are some variants of EVs for the same variant of a petrol IC engine vehicle. And we can see that the electric vehicles are almost double the price. And it also required a very high size of battery. And as we can see that India's emission regulations are very high nowadays. So to reduce that, it will require some after treatment, and it will increase the running cost as well as the fixed cost. Where you can see that for the case of hybrid electric vehicle, with the increase of almost 20% of the price, we can reduce the running cost by almost 40%. And also there is an improvement in the mileage as well. But also we need a very low capacity battery, because it is assisting the IC engine vehicle, and as we are reducing the usage of the engine, so we are also reducing the emission as well. And also it is visible in the market also, that is whatever the EV sells, it is almost 2% of the total vehicles sold till in financial year 2022. And this is also not utilized properly for the FAME 2 fund. So if we can make a cost-effective hybrid vehicle with the efficient energy management, it will be sellable in the market. Means in this research, we will talk about different kind of energy management strategies which can be implemented in real time. Not only that, it can also consider many factors that we will discuss in this presentation. And in this topic, in this presentation, we will only talk about that P1, P2 parallel hybrid electric vehicles, where the P2 hybrid vehicle is where the motor is connected with the same shaft with the engine through a clutch, and the transmission is connected with another shaft of the motor through another clutch, and that output of the transmission is connected with the wheels through the differential, and each of the component has its own controller, and there is a VCU, that vehicle control unit, which is controlling all subsystems, considering many factors like operating points and its temperature, its fault conditions, many things. And so in this kind of vehicle, so we generally have 5 modes. Means one, there is an engine alone mode, where engine only running the vehicle directly, where motor is not participating in this and in the hybrid generating mode, where whatever the total power or torque is required from the driver, engine is generating more, so that motor can be used as the generator, and it can charge the battery based on the requirement. And another mode is the hybrid motoring mode, where the motor can assist the engine and share the total power demanded from the driver. And another one is the hybrid motoring mode, EV motor only mode or EV mode, where only we can use the battery and motor to run the vehicle. And the last one is the very important, that is the regenerative braking mode, where during the braking, some amount of the braking power we can also provide through the motor to the vehicle to stop the vehicle. So these are the 5 modes, but when to use which mode, that is very key for the overall performance of the vehicle. So this is the overall architecture and hierarchical supervisory controller levels. So here we can see that there is a lower level controller, where each component has its own ECU or controller. Like engine have ECU, means engine control unit, transmission has its transmission control unit, all these things. But to run all these things, means engine, motor, transmission, battery, brake, everything in an efficient way, we should have a VCU or vehicle control unit. In the VCU, in generally, there are many functions like thermal management, diagnostics, startup shutdown sequence, then torque structure, where it takes all the input from the driver, ADAS, and ESCs, and it generates the net torque demand and gives it to the energy management system, where the energy management basically splits the power between engine, motor, and selects the gear and gives the brake command such a way that for the overall journey, that energy can be minimized. So this is one factor. So this is the automatic control loop, and this is the command loop where the supervisory controller takes the input from either ADAS or driver and then generates the torque demand and giving it to the energy management, and then it is commanding the lower level controller. And for the adaptation loop, so this one we can also consider the trip level information and also ADAS and various other factors like leader and other sensors, and accommodate in this energy management strategy. So in this thesis, our contributions are mainly in this, that short range prediction horizon based technique, and the conventional short range prediction horizon based techniques does not consider the trip level information. So we have incorporated the trip level information in the short range prediction horizon based techniques and also published to international conferences. And also the conventional ADAS also don't usually interact with the VCU or energy management and takes the decision. So here also another contribution is there, where we have also applied a patent also, and inside we have also improved the performance of the computational complexity of this short range prediction horizon based techniques. So these are the things we will discuss in the following presentation. So this is the main objectives of the short range prediction horizon based techniques. So it basically splits the power between the total torque demand of the driver, between motor and the engine, and based on these splits, it can operate in different modes, already what I have explained in the earlier section. And its main objectives are to maintain the drivability, means whatever the driver is demanding, we should provide that, and minimize the energy consumption, SOC tracking, considering all the motor torque limits, speed limits, engine torque limits, speed limits, and SOC C-rate power limits. And its control variables are engine and torque. And here in this thesis, we have considered that gear commands are generating from the separate rule-based strategy. It is not part of the optimization. So here I am just giving an intuitive approach that if I will split the torque from a torque, how it affects in the operating points of the engine and the motor. So here we can see this is the current operating point of the engine and the motor. And here the assumption is gear is constant and vehicle is running at the steady state. So speed is also not changing. And operating points of the engine, if I do the torque split, so what will happen? Because as it is, I can see that as it is a P2 hybrid, it will change only on the same speed, because it is a coaxial, means motor will run at the same speed of the motor. So it will change in the same direction and either improve or decrease the overall efficiency of the motor and the engine. But it depends that which operating point we want to choose. So here, this is the new operating point. But the question is here, that is this decision, because we can see that this is a nonlinear operating point, and this is also a nonlinear efficiency maps, and this is also nonlinear V-shape curves. So through this, we have to choose optimal operating points every 10 milliseconds based on the VCU's requirement. So that is the challenge we have to solve here. So if we also split the gear, so we have, for the different gear, we have our shaft speed will also change. We will have different kind of operating points here. So among these operating points, we have to choose that which one is the most optimal, and how to choose these based on the trip level information. So this is the challenge, but to solve this, usually it is a very famous algorithm we usually use, that is the ECMS algorithm. It is an instantaneous optimization technique, which will minimize the equivalent energy of the motor and the engine together based on this state of the SOC, and considering all these constraints and equality constraints. But this ECMS technique does not take predictive action based on the velocity prediction, as well as it does not interact with the trip level optimization, what I have already discussed in the past section. So to solve this issue, we have considered two very well-known problems. That is, one is the zero emission zone, and another is the varying grade. Means what we are considering, that in this zone is the zero emission zone, means ideally the vehicles only EV should run, or in the case of HEV, it should run only using the motor, with the help of the electrical energy. In this region, vehicles should not use the IC engine. But the problem is, as the normal conventional strategies does not consider about these informations. So if my battery is depleted during these zero emission zones, so it have to start the engine during this. So it will violate the condition. And for the case of varying gradient, it has to maintain the drivability. Means before this varying gradient zone, if my SOC is depleted, then engine cannot take the assist of the motor, and it may also required driving torque also may be required from the motor to assist the engine. So that is also not possible. So that problem we have solved, and also published 2 international conference papers using this problem. So this is some cost function, means how we have improved the existing ECMS and modified it for the case of ZDZ. But here some interesting results are there. That is, we can see that here this is the drive cycle, and here this is a small grade, there is a big grade is there, and the blue one is our normal ECMS algorithm, which we can see that after almost 15 kilometers, means where the grade is started, it has stopped. But although both of the algorithms started with the same SOC, and here it has stopped, but here our algorithm completes the grade without changing any architecture of the vehicle. It overcame the grade and it completes the drive cycle. So without changing any architecture or size of the vehicle or just size of the engine, anything. And here also we can see that with the normal ECMS, the engine has to start in between the ZZ zone. But in the case of modified ECMS, we can take the predictive action it can complete the full ZZ zone without using the IC engine. So another problem we have solved, that is, we can note that there are a lot of informations are available during the using the traffic light information, various sensors. We can little bit predict the future velocity with the help of many algorithms. But actually, we can take the advantage of these futuristic informations with the help of many algorithms. Here, the thing is, there are a lot of options are there, and we can choose that which one is the optimal one. And based on that, we can select the top speed ratio such a way that overall journey's energy optimization can be minimized. But here, the full drive cycles informations may not be required. Means we can, because it will increase the computational complexity. So for the MPC, that model predictive control architecture, we can reduce the prediction zone and reduce the computational complexity and solve the problem iteratively, such a way that we can take the advantage of this predicted information. So here there are some formulations for the model predictive control based energy management strategy. What we can see here, there are a lot of nonlinear dynamics is present in the formulation. So here, this is the SOC dynamics is nonlinear, and vehicle dynamics is nonlinear, and also the VSFC curve of the engine and the motor is also, and it is also nonlinear. So there are lot of techniques are there, means how to solve this kind of problems. And we can also solve using that linearized LTP MPC, linearized version of the MPC, and also the nonlinear MPC. There are many methods out there. But the problem is linear in the literature, whatever the implementations are there, so linear MPC is real-time implementable. But but at the cost of accuracy, means we can reduce the performance. The performance will affect. So that's why we can increase the performance with the help of nonlinear MPC, but at the cost of computational cost. Means it will take so much computational cost that it cannot be implemented in the real time. So for this problem, we have implemented a new strategy, that is model predictive static programming. So this is a iterative method and recursive method. So where it can solve this kind of nonlinear dynamics in much more faster way. So it has implemented earlier on aerospace and the robotics applications. But here, here it never have been applied for this kind of problem. So we have applied, this is the pseudo code for this. These are the formulations, means for the sake of time, I am not going into this. And there are some interesting results we can see. That is, here we can see that with respect to dynamic programming, it is giving almost very good result, that MPSP. But in the case of LTP MPC, means linearized MPC, it is performance is worse than the MPSP. And this is the another SQP MPC, it is the another nonlinear MPC, it is also giving similar performance. But also we can observe that as we are increasing the prediction horizon, it is also improving. And also we have tested in the real time. But why this performance is improving? Here we can get the answer. Means here we can see that prediction error is much more higher. Prediction error is much more higher for the LTP MPC, whereas it is very low for the MPSP and SQP MPC. Here also we can see that. But when for the case of real-time implementation. So there we can see that it's real-time execution time. It's almost half of the LDB MPC, and it is the SQPS MPC is the 7 times. So out of this result, we have also published a journal paper. So another problem. So what we have solved, I have already told earlier, that is the ADAS-based energy management. So here we can see that ADAS, conventional ADAS feature does not consider the fuel consumption and energy consumption, emission, SOC, all these things. And also for the case of energy management, it does not consider the safety aspects of the vehicle. So we have merged these two problems and solved, and also we have applied a Indian patent and international patent for this. So this is the detailed block diagram of this, means what the level 2 optimization is the ADAS based optimization, and level 1 optimization is the trip level optimization. So here we can see that what are the factors the level 1 optimization is considering, that is the speed, SOC, gear, space and time headway from the sensors, and also the set velocity, and it is generating the optimal velocity which is around the set velocity without deviating from the set velocity, how it can be operated. And also we have also incorporated the traffic light information, how further we can improve this performance with the help of traffic light information. So these are the some pseudo codes for this implementation. Here, as I told, means we have also incorporated some traffic light knowledge, traffic engineering knowledge to solve this problem. And here also we have incorporated some traffic light information to improve the performance. Here what we have done here, we have from the GPS Google map, we have selected up 2 places from in Kolkata and got the GPS data and reconstructed the drive cycle for the both of the routes and ran our algorithm, means without our novel architecture, how it is performing, and with our novel architecture, how it is performing. And also we have also created the algorithm such a way that it can operate in different modes, like eco mode, where it will optimize for the fuel consumption, minimize the fuel consumption, and for the sports mode and mixed mode. Means sports mode, it will focus on the time of the travel, and mixed mode, it is a Pareto optimal solution for the both. And here means in these 2 orange regions, this is the where our traffic light is present here, what we can see here. And here we can see that it will not only cross the traffic lights and operate in the different modes, it can also minimize the energy. And here also another thing is there, we have also incorporated a lead vehicle, which will sometimes it is coming near of the ego vehicle and it is going away. So here, this is the blue and black line is the lead vehicle for both of the algorithms. And here some of the zoom part is there, where you can see that here where the normal vehicle without this feature, it is actually stuck here in the traffic light, where our algorithm it basically does not stop, but it reduces the speed and then it went down. It don't have to stop at the traffic light. And also with the in the case of lead vehicle also, it can able to traverse this whole space. And also we can save the energy for these different modes. But here in the case of lead vehicle, with the presence of lead vehicle, there are some up to 3% we can see the improvement with respect to different drive cycles. But without the without the presence of lead vehicle, we can see there are almost 10 to 13% of improvement we can observe. And here, this architecture also we have implemented in real-time popularity. So these are the some implementation picture where we have implemented some of the algorithms in GCM 196 and also some of the algorithms in this PI board. So we have communicated through the CAN communication, and this is our OpenRT setup where this is the CAN communication and this is the CAN simulator block, and this is the OP5700. This is the real-time simulator. And this is some of the pictures of our real-time simulation. And these are the some publications we have done. So this is the international conference paper. This is one paper, a journal paper we have published. This is, we will communicate very shortly. And here, this patent for the last work, we have applied for the 2 patents. Means one is Indian patent, and another is international patent, and along with Tata Motors. Because this project, this hybrid vehicle project, we have worked with the Tata Motors. Thank you.